Good afternoon, class. My name is Robert Skinner, and I am an electrical engineering student at Wayne State University. So since I'm an electrical engineering student, I delve into circuits, voltage, Ohm's law, all the good stuff. And so I decided to base my project off of 3.5, which deals with electrical circuits. Now here you'll see that we have Kirchhoff current law, which is basically just truth theorem, and then we have Kirchhoff's voltage law, which we will again delve into later, dealing with different equations. So according to Ohm's law, right here, we have the voltage drop, which is in a circuit, as the electricity or power source goes through a circuit. There is R, which is an existence, and I is actually the current, which is how much power is going through the whole circuit. And we can equate this as ER, which is voltage drop, equals resistance I, resistance times I, which is R times I. And then we also have another form of voltage drop, which is EL, across an inductor this time, which is proportional to the instantaneous rate of change of current I. So EL is the voltage drop across an inductor. This L is the inductance, and this is the rate of change of I, which is the current. Now, the voltage drop across the capacitor is proportional to electrical charge Q of the capacitor, which is given by this formula right here. We can call C the capacitance. And just right here briefly, this is a table of all of our variables and what they mean. And as I scroll down, I'll briefly show you the examples of using the equations to find certain things like current, voltage drop, or even inductance. Now that you have a brief understanding on currents and inductance and voltages and trying to solve for it, we're actually going to solve this question right here. So, an RL circuit with a 5 ohm resistor and 0.5 inductor carries a current of 1 amp at time equals 0, at which time a voltage source E of t equals 5 cosine 12t volts is added. Determine the subsequent inductor current and voltage. We have our question. Now, let's solve for it. For this, we'll use Kirchhoff's voltage law, given as L, change in current over time, plus resistance equals E of t. Okay, so here, we know our resistance is 5 ohms. We know our inductance, which is given this time. Luckily, we don't have to solve for it. So we know our inductance is 0.05, and we know the function of the voltage source, which is 5 cosine 120 actually, I'm sorry, t voltage. And we know at time equals 0, our initial current is 1 amp. So I of 0 equals 1 amp. Now quickly, if we substitute all of our knowns into our actual equation, we get 0.05 di dt plus 5i equals 5 cosine 120t. Right? Okay. These type of model equations, we always want to try to put it into the first order. So for us to do that, I'm just going to divide everything by 0.05. 0.05 on both sides. 0.05. Oh, sorry, no, wrong one. 0.05, which will give us di dt, okay, plus 100i this time, since we're dividing by a decimal that is smaller than 0, mind you, which equals 100 cosine 120t. Okay, next step is going to be a little weird because dealing with currents, total current is divided into two different parts. It's something called the transient current and the steady state current. So it's actually total current is the sum of T is equal to, I'm going to use the term homogeneous, which is something you will learn later down the line. So you can use a capital I, lowercase I, doesn't matter. But for this instance, use lowercase I h of t plus I p of t. So this means the total current is made up of a sum of the transient, which is homogeneous current equation, and the steady state, or particular solution current. In this case, we're going to focus on the homogeneous part so far first. So we have di dt plus 100i. In this case, instead of this, we have 0. So let's do that. We're just going to try to go ahead and isolate the dit. And then if we do that, we will get di over dt, or no, sorry, just t this time. It's going to be equal to negative 100i. And then we're just going to integrate both sides. It's going to be a little weird to integrate both sides. And actually, you can actually write this as 1 over t di, and we already know what that is. It's common. We get ln t this time. Forget that. Equals e get of 100t. Well, there's a c there because when you integrate and you just have this, you literally have to add c. But in this case, it's an option you can add or not. It doesn't matter. But in that case, we have our homogeneous one right here. Since our regular function of steady rate current contains a cosine 120t, we can somewhat break the rules a little bit and infer that the actual particular solution will contain a sine as well. But we just don't have the two coefficients that go with it. This can be written as, I p t is equal to a cosine. We just use a and b just as placeholders until we figure it out. Cosine of 120t plus, can't forget the parentheses, so important, b, again, we don't know the number yet, but two different numbers, sine 120t. All right. Our next step simply is to just derive this so we can make it a little easier to digest and to place it back into our differential equation. So we will derive the first term, just a cosine of 120t, which we simply know is literally just going to be, bring out the 120, get negative 120a sine of 122. For the second term, b sine 120t, we get plus 120 cosine b, or sorry, 120b cosine of 120t. Second differential equation, we get 120a sine 120t plus 120b cosine of 120t parentheses plus 100 times a cosine of 120t plus b cosine 120t, all equal to 100 cosine 120t